All right. Welcome, everyone. I think we'll give it another minute or so to get things set up. A few little minor technical issues, so we're starting a little late. Get started here very soon. Thank you all for attending. All right. I think we will go ahead and get started then. So welcome, everyone, to our next ISEA webinar. We're happy to have Dr. Bianca Maria Colissimo with us today to present on in situ monitoring I have the title right here. Sorry, things are kind of in the way. Situ monitoring, control, and advanced manufacturing. Before we get into that, a couple of little quick announcements here. So first, after today's webinar, we will have another one coming up soon. So this will be presented by Fadel Megahad on the use of generative AI for quality. So that'll be an interesting one. Stay tuned for that one. That's coming up in May 20th. We're still working out details there. So once we have those, we will pass them on to you. And again, as a quick reminder, ISEA, the International Statistical Engineering Association, is sponsoring this webinar. I'm Caleb King. I'm the current chair of the International Statistical Engineering Association. If you want to find out more about our organization, be sure to check out our website, ISEA-Change.org. You can also reach out to us at info@ISEA-Change.org. If you would like to present a webinar, again, reach out to us. We'd be happy to work out with you. And if you more importantly, if you'd like to become a member, definitely visit that page. Here's a little hint, it's free, so don't let the finances stop you. We have a lot of exciting things planned for this year, so be sure to check them out. You can look at our About ISEA page to find out more about us and a quick hint at some of the things coming up. So with that, though, I'd like to go ahead and get started to today's presentation. So with that, I'll switch things over here to Dr. Colissimo. And while she's getting things set up, I will do a brief little intro for Dr. Colissimo. There we go. Okay. So, all right. Dr. Colissimo is a full professor in the Department of Mechanical Engineering at Politecnico di Milano in Italy. It's in Italy's leading engineering school, ranked among the top 10 universities worldwide in mechanical, aerospace, and manufacturing. She received her Master of Science and PhD in Industrial Engineering from Politecnico di Milano, and following her PhD, spent a postdoctoral visiting period at Pennsylvania State University. She's currently a visiting professor at the Massachusetts Institute of Technology. Her research focuses on big data mining in Situ monitoring, which we'll discuss today, and process control for advanced manufacturing, with a particular emphasis on additive manufacturing and bioprinting. She actively contributes to a number of leading scientific journals in the field. She's the department editor of IISC Transactions, a senior editor at the Uniforms Journal of Data Science, and editorial board member of Journal of Quality Technology, where she previously served as editor-in-chief. She's also senior editor of Progress in Additive Manufacturing and editorial board member of Additive Manufacturing Letters. In 2023, she received the George Box Medal Award, the ASQ Brumbaugh Award, and the award from the Royal Swedish Academy of Engineering Sciences, and the International Process Engineer Award for powder bed fusion. And lastly, she's recognized amongst the top 100 Italian women scientists in STEM. Quite to the record. So we're happy to have Dr. Colissimo with us, talking about in situ monitoring and control and advanced manufacturing. So Dr. Colissimo, I'll hand it over to you. Thank you.
Thank you. Thank you for inviting me. I'm really, let's say, excited of being here today because I mean, this connection between data science and industrial engineering and engineering has been always leading all my recent interest. So this is just to make a recap on my university. So I like to point out the rankings, especially because the rankings depend on the also on the employer reputation. We are really highly ranked in employer reputation, and is always some sort of marketing for our students. So in case there are students from Polimi that are interested in joining your group, I suggest just to take a chance to have them joining the group, because they are supposed to be good, let's say. And the other side, as was mentioned, is this my connection between, on the one side, the additive manufacturing and the advanced manufacturing world. On the other side, as you can see in my small CV, you'll see a couple of colors. The red one represents my hardware part. So as you will see, I'm also co-leading some labs. And the other side, it's my more data science side, which actually the main message is that if you are interested in combining these two worlds, there are a lot of opportunities for solving real problems that require a lot of data mining. So it's really interesting, the interconnection between, let's say, the manufacturing world and manufacturing problems with respect to data mining problems that are nowadays, let's say, a common problem faced by people working in manufacturing. So these are the three, let's say, big elements of my recipe and my main magic recipe for my CV and my research interest. So on the one side, there's all this data science community, and I want just to, let's say, follow the previous introduction, saying that Informed Journal of Data Science, Journal of Quality Technology, and the IIC transactions, together with all the other, let's say, journals, are really interested in having good papers that are showing the interplay between real industrial problems and new solutions coming up from the data mining side. And I also want to mention that I have some connection on the manufacturing side. This is why I'm today here at MIT, because in this semester I'm teaching a course on additive manufacturing in the MIT department here at MIT. But what is making really my research very interesting in terms of research challenge is depending on the labs. So I will just spend a few words on the labs that I'm co-leading together with a lot of, let's say, friends and colleagues. One, it's more on the metal side. It's called ADMI Lab. It's a metal additive manufacturing laboratory. And the other one, it's the newborn, and it's mainly on bioprinting. So the main difference is that, additive manufacturing traditionally is working with a lot of different metals. And so here are all the solutions that we have in our lab. As you can see, the process is quite open, can have many different principles for spreading powder and melting powder, which means at the end being able to create really complex shapes. And we will have some time just discussing what this complexity means from the viewpoint of quality. The last one solution that I'm showing, it's the new arrived machine that is a multi-material machine. So in this case, you are not just deciding at each location what is the shape. So if this location should be full of material or empty, which is the big advantage of additive manufacturing, you can really create a volume where you decide where to put material and where don't put anything. But on the other side, you can even now decide what type of material you want to play with. So in different locations, you can at least in principle create parts with many different materials without any joining, which means a lot of pain, because actually there are a lot of, let's say, defects in those parts that look beautiful. In this case, it's copper plus two different alloys, steel alloys. But there's a lot of mess in trying to find the best process parameters on the one side, and on the other side, being able to avoid defects at the end. All these processes have different pros and cons, and what we are doing, and I will show some example. We are also creating some small prototypes. For instance, this was a prototype that was developed and patented a few years ago, and the aim was the perfect machine. So this yellow box that is going back and forth is supposed to kind of cancel the defect, since the idea of the additive manufacturing is that layer by layer I'm building a part. The main idea of Penelope, this prototype, is when I see that there's a defect at a given layer, thanks to all the camera, and we will discuss about all this, let's say, sensing, what should I do? I can first of all stop and avoiding, let's say, building a huge part that is defective. But on the other side, the idea is that I can maybe even correct the problem, so erasing the last layer with the defect, and so start again going up. So it means that at least in principle, I should be producing part without defect at all, zero defect manufacturing. The newborn, as I was saying, it's quite a real interesting adventure, because in this case, we are bringing all the in situ monitoring and sensing and data mining in the world of producing living tissue. In this case, the main idea is to combine a bioink with living cells, maybe stem cell, that are going to be deposited depending on the process. There are many different processes. The three examples of processes that I'm showing in the video on the bottom are the ones that are in our lab. Despite of the specific process, the end of the story is that I've been printing, 3D printing, living bioink plus living cells. So at least in principle, I should be able to print skin, bones, cartilage, and maybe in the long run, we're also trying to create something more complex like small organs. And this field of research is quite interesting because there are a lot of opportunities in drug, let's say, research, in vitro disease models. So I mean, I'm bioprinting some small tissue in one chip, so that I can even see how the chip is reacting or changing depending on the type of illness or the type of effect in terms of drug, without going, let's say, directly to experiment with animals, or let's say in vivo. And there's, in the long term, the idea, obviously, also of the organ transplantation, so that I'm receiving my own organ with my own cells, so avoiding rejection. And so this is going to be the possible future of the organ transplantation, as there are less and less organs available in case you need this type of transplantation. So I was mentioning two labs. One is ADME, so all the machines for doing additive. One is the previous one, 3D Cell, which is the bioprinting. There's the third guy, that is IC Labs, which is exactly the labs in which we are collecting all the data from this 3D printing, additive manufacturing, and bioprinting labs, and just playing with the data. And so I will mainly show all those data and all the, let's say, type of solution that are needed, because are problem driven with respect to, as I'm saying, image usually. So we will spend some time discussing about image that are representing the quality of the part that is being produced, 3D point clouds, or video, in case I'm trying even to capture the dynamic of the process, and you can see that the dynamic is quite complex. And video also in the bioprinting side, that looks a little bit easier to be detected, but has anyway some additional and different problems to be solved. So I will spend my talk just focusing on what are the data-driven challenge that this type of advanced manufacturing or additive manufacturing solution are looking for in terms of needs and research questions that are posed to the community. So just as a short recap, I will just spend a few words on say why I think that additive and in situ monitoring in additive makes sense and is interesting and is going to attract the interest of research in the future. Then I will just show some examples coming up from image-based analysis, video image. It's going to be the third, let's say, step, and then I will arrive to some conclusions. So why additive manufacturing? First of all, because there are many different sectors that are interested, even if the technology is still too expensive for becoming, let's say, a massive, let's say, use of additive, but for sure is interesting in the aerospace. and space, it's gaining a lot of interest and a lot of attention. It is important also for the high level, let's say, automotive, so racing cars or very expensive cars, because the key, just looking to what is in this slide, key issue of additive is that it can create very complex shapes. So in case you need complexity, you need to do something on this complexity in terms of shape, you can go with this technology and create some parts that you cannot produce with any other conventional process. You can enjoy this type of solution also for, let's say, creative industries like jewelry, or this is another important sector for health. So all the prostheses or implants. This is a well-known testimonial of additive manufacturing. That is the hip implants. The reason why additive is so interesting also in the healthcare let's say research, is because you can, at least in principle, realize personalization quite easily. So I can just change the design, define the type of let's say shape that is good for my bones and my body, and then just go to print without any significant cost in terms of tooling, because I mean, I can really make one of a kind production easily. So I don't need to have lot productions to make the manufacturing process profitable. And also in the molds, which means machinery, you see the example that I'm trying to show in the bottom with all these channels with many different colors. This, it's called conformal channel. Conformal cooling means that I can create this empty space, this empty shape and channels inside the mold quite easily. I cannot do this type of complex channels with any other technologies. And usually this means that I'm able at the end to make a mold that is long lasting and has a better performance in the bar that is being produced. And so there's a lot of opportunities also in the field of machinery for using this technology. The technology is quite simple in the way it works. So it starts with the complex shape that you have been designed to produce, just slicing in small, let's say, layer. And then going into the machine, I'm spreading powder, I'm maybe preheating the powder, and then energy, it's going to melt selectively the powder in the location in which I want to have a solid at the end. And then layer by layer, I'm creating the 3D complex shape with the shape that I want. The end of the story is that I'm getting rid of the powder that has not been melted, and I'm able to arrive to the final complex shape. The key issue of the technology is the graph that it's shown on the right hand side, that is describing how complexity of geometry. The blue line represents the cost per piece as a function of the complexity of the part that I need to produce. So as I was saying, the blue, the growing one, it's showing that with conventional manufacturing, so all the other existing processes, usually if I want a very complex shape, I need to spend a lot of money for the single part to be produced. So there's this exponential increase of cost per part when you want to create a complex shape. The other line, the green one, which is basically flat, it's showing what is the cost per part versus complexity for the additive manufacturing technology. As you can see, this type of technology is quite insensitive to complexity. So it means that if you find a reason to have a complex shape at the end, additive manufacturing is the technology for you. Clearly, if you want to produce very simple shape, it's not going to be, let's say, interesting from a viewpoint of the business of the company, because cost per part means really being able to survive or being competitive. So in this direction, assuming that you are interested in complex part, which means space, aerospace, or machinery and tooling, or oil and gas, all these type of sectors are more and more often using additive manufacturing. There are a couple, let's say, of paradigm shift that I see. The first is that since you are able to produce complex shape, you are going to take advantage of this complexity. So if you think about quality, just even quality inspection, but quality monitoring, it was an easy and not so easy job, even in conventional manufacturing, dealing with some simple shape, like the first example, it's a simple cylinder in which I'm just measuring the diameter with time and just being able to detect some anomaly when the cylinder has an unusual diameter. But just try to replicate all these idea that has been moving to profile monitoring, surface monitoring, so is also able to maybe capture the 3D point clouds in producing parts. But if you think about what I'm able to produce with additive, this complexity is going to create a lot of problems in even identifying if the part is defective or not, or being able to identify it out of control in case you are producing more than one part and you have some sort of sequential production. So first of all, complexity is nice, but requires a totally new set of tools for dealing with quality for complex shape. And the other second paradigm shift is that you can really enjoy a lot of information that is in the process while the process is running. I'm just discussing about multiple signals, image or video image in the visible or thermal range. So this is the other big, let's say, challenge. Instead of just waiting days or even weeks sometimes to arrive to the final part, why don't we take into account all the data that we can gain and add in basically real time to detect defects that are going to produce a problem at the end. And this is from the viewpoint of a company. So we have a lot of connections with end users. It's quite interesting because they don't want to spend money and waste material and time for a bar that has some defects in the first few layers, just waiting 1 week to discover that the defect is there. So the advantage is clear, being able to anticipate defect or even compensate for the defect as soon as you see something there. But on the other side, you have these tons of huge amount of data. You can be killed by the amount of video and image that you need to, let's say, try to analyze in almost real time to be able to detect that the problem is there. And so the key point of in situ monitoring is, instead of just changing, maybe even understanding or making some process optimization, changing all the parameters of the process and just looking the end of the story, which is the product, just take advantage of what is called the process signature. There are many different types of signature that you can look at when you are printing a part. So to reduce cost, time, and especially this is quite interesting for highly regulated sectors. So zero defect is a must if you are doing aerospace product or if you are doing live health or implants, so medical, let's say, product. So I was just doing the job of looking to the recent literature on in situ monitoring and additive. And I mean, just looking to the last 10 years, you can see that there's this exponential growth. These are just a Scopus, let's say, plot that is just showing all the papers that have been published recently with in situ monitoring and additive manufacturing. And as you can see, I was surprised to be still the first most prolific author, but I think I've been using consistently the terms in the papers that I've been producing. But there, as you can see, it's a worldwide challenge, because clearly if you are able to make some machines that are more intelligent, or even helping the end users in producing parts without defect, this is going possibly to even act as game changer for this technology that has still a lot of stability problems. And as a matter of fact, there's a recent report, maybe you are interested in downloading, because it's a free report from ASTM, the American Society, that is just trying to define also standards, and the NASA, just describing about the strategic vision on additive manufacturing and in situ monitoring, what is the technology readiness level. And again, the most, let's say, interesting and ready to go technologies are dealing with optical imaging, thermal imaging, so it means or spectrometry. So it means a lot of video, image, and this type of complex data. And so I will just show some examples on problems that we have been trying to solve, and maybe even ask for your help on solving the new problems that we are trying to face at this point in time. So I will start with some examples on the image. And one interesting example that I like to mention is this idea of just taking picture after the layer has been printed. As I was showing, layer by layer, you are creating the final shape. And so our idea is, instead of just going to the final inspection, X-ray CT, usually you are doing computer tomography at the end, why don't we just take the picture, trying to analyze what is the shape of the layer, the printed zone in the layer. And in this case, I'm just showing one example in which I'm starting from the image of that the parts printed on one specific layer. You need to make some image analysis, and we have been trying to play with many different algorithms, both, let's say, coming from traditional statistical approach for dealing with image analysis, but there are a lot of new tools coming up from the AI world, and the transformers and the foundation models, even with a small amount of training data, you can do a good reconstruction at the end. And then the end of the story is, once I've been able to kind of define the edge of the geometry printed in one layer, why don't we compare this actual geometry with the nominal one, the one that I have in the design of the part that I was supposed to print at that specific layer, to identify deviation. So the deviation from the printed layer with respect to the nominal shape, it's going to be possibly a defect if this deviation is large enough to, let's say, show some problems at the end. So what we've been doing is saying, okay, let's move in the direction of some sort of statistical process monitoring or a control chart for doing this job of detecting the layer that is out of control in terms of the deviation of the printed zone with respect to the nominal one. And we have been enjoying a lot of, let's say, challenge, first of all, because, I mean, once you are doing this reconstruction job, what is the type of measure you are using for the deviation? We have been start defining and deciding to work with the max deviation of the real with respect to the nominal. So maybe in the second example, there's some part that has been not printed, so there's the deviation. They're missing material on the top of the image in out of control. So in this case, we have been decided to work with the max deviation, and so doing some fitting of the Gumbel distribution of order statistics as the main, let's say, in control state, and then being able to identify the, let's say, threshold just by looking to what is the Q of this Gumbel distribution fitted in our, let's say, sequence of layer. And we've been showing that this is quite interesting, maybe even combined with some self-starting solution for detecting real defect with a good, let's say, capacity and capability of just having a slow and small false alarm rate with respect to being able to actually detect the problems as soon as we see some deviation that has been created at one specific layer. So this control chart is basically showing how can I just detect problem, and what is changing on X, it's the layer. So instead of having time instant that are the sequential part produced, these are time instant that represent the sequential layer that I'm producing in this layer-wise production of one part. But again, just to go in the direction of being close to real problems coming from industry, as you can see, we are not printing cubes, so we are not printing simple shape. We have been trying to really investigate problems, existing problems. This is a, let's say, a bracket, a supporter for a mirror that should be go to in with the European Space Agency in a mission for let's say being able to have the right sensor and the right mirror in space. And in this case, the shape is complex. The object should be lightweight because you can see that everything that is moving and flying, but in this case, even going to space needs to be really, really light. And so the object has this lightweight structure, but in a given location, we were experiencing some problem because the change of the geometry in one specific location was maybe too challenging for the technology. And so what we have been saying, okay, assume that there's a defect over there. What if the defect shape and size is increasing, and especially the size is increasing? So what is our capacity in terms of in situ monitoring of detection different size of the defect? This is just to show how really engineering problems are combined with data mining and are combined also with inspection solution and metrology, because we have been trying even different types of in situ sensor. So we have been trying to go with the traditional solution in which the camera that is taking the picture is outside of the chamber. We have been deciding, okay, let's play a little bit with an open machine where we place the camera where it is really needed, close to the laser scanner. And so we are doing a better job in the image. So it's like playing the game with the glass that you are using for looking to the defect. But we have been even patenting a new solution that is in our lab. Our idea has been just to use the same idea of the scanner that you are using for taking a copy of documents in your office. But instead of mounting this scanner on your office machine or office printer, we have been mounting the scanner inside the machine, letting the scanner take an image of the last printed job while the powder has been spread. And so it means that in, let's say, hidden time, you are, thanks to this scanner mounted on the recorder, taking an image of what was the final geometry of the part. And this is totally changing our resolution in terms of detecting the deviation with respect to the nominal shape. The end of the story is that we have been creating some probability of detection curves that, depending on the defect size that is changing on the x-axis, are just showing the different type of architecture. The green line is this new scanner that we've been developing in our lab, and is showing that even small defect can be 100% detected with this new sensor. But the blue line, it's what you can do with a traditional camera outside the machine. So you can even detect larger defects with good probability with some industrial solution existing as it is now, just putting a camera outside. So what I really like to emphasize is that we really need to provide some sort of numbers to companies that are able to combine the data mining tool that we are using, the type of sensor, so the type of data that you are playing with, and these free sensors are changing the type of data you are playing with. And it's also really important to be robust in the information. So in case you want to detect a small defect, the actual machine with the actual camera mounted outside is not the available and the right solution. In case you want to have a small defect, you need to change the machine and the sensor. Or you can even try to play a little bit better in terms of the data mining solution. So what I'm saying is that for being able to attract industry, we really need to be precise in what are the actual pros and cons of the existing solution on the market, and maybe even doing research together with them in finding some new solution. I'm getting close to the end. So what I would like to just show is that we have been doing a similar job, but making it a little bit harder, trying to investigate in situ monitoring of lattice structure. Lattice structure are these strange shape made of full of voids. It's just a cell that look like a cell with empty space and material that is repeated over and over and over. This type of geometry can be just produced by additive and are quite interesting for vibration absorption, for very thermal cooling capacity. So are in many different, let's say, applications in, again, space, aerial, racing, machinery, or bio implants. And it's some sort of new, they are also called metamaterial. It's a new type of, let's say, playing the game or architecture material that I think are going to be more and more interested in the future. And again, here the job is a little bit more challenging because we are just taking a picture of this complex shape, even if it is some sort of ordered shape. In this case, what you can see is that this lattice can be sliced as we are growing along Z. So this video that looks like flowers that are opening and then going back to be just a dot are just the lattice structures seen as different height, different Z. And so it looks like a video, but it's just a sequence of frames showing this lattice at different height level. And so again, the idea is how we can simplify the geometry, such a complex geometry, in some sort of very easy to be handled way. And here the idea was, okay, let's just play the game of comparing again the real geometry at each layer, so this sort of video, with the nominal geometry at the same Z. So these flowers represent the nominal evolution of the printing of the lattice as Z is growing, so moving along Z. And so we have been saying, okay, let's just play the game with the difference between what is the real shape at each layer with respect to the nominal shape. And let's just ask us the question, are you able to detect an anomaly in one cell? So understanding if there's one specific cell that is out of control in terms of the natural variability that I'm used to see in this printing job. And here the basic, let's say, trick is that just look into the sequence of deviation of material printed with respect to the nominal shape for one single cell in one specific location. So I'm just focusing in one part of the lattice. We have been able to basically translate this sequence of image of deviation in a profile. And as you know, there's a lot of nice approach for functional data ANOVA, functional data monitoring, functional data everywhere. The way in which we have been transforming this sequence of deviation image in one profile, it's just summing up at each specific deviation, at each specific Z, so each frame of this video, just summing up what is the overall let's say, intensity of this pixel, just summing up all the pixels, which represent the overall deviation observed at that specific location for that specific cell, and just doing this reconstruction as a function of Z, of the height. And so the end of the story is that I'm able to represent one geometry, printed geometry of one cell as a profile. And then we have been just doing our profile modeling using this spline, and then doing some SPC stuff based on this spline. Just one comment. Sometimes you are just trying to do some simple exercise once you have been defined in the way of simplifying the problem, like in our case, translating a complex geometry in a profile. There are some problems also layer-wise. So what I can observe in one layer is different from what I can observe in the sequence layer, because depending on how the laser is doing his job, there's this difference in the contrast between the dark, the printed zone and the loose powder. So this difference of brightness of the image, I'm just showing two different images. One is dark field image and the other one is bright field image. And they are coming from the same machine, same job. It's just the height and the illumination condition and the laser scanning strategy that are making this difference. So this is where we have been even thinking about being able to kind of normalize this difference using a weighted B-spline fitting, where the weight is exactly doing this job of normalizing the specific contrast in the image. And we've been able to show that by doing this B-spline with weighted that are just taking into account the layer-to-layer variability of the image, we are able to have an in situ reconstruction which is almost perfect. I mean, the error with respect to what you can do offline with X-ray CT, the deviation of with respect to what you can do in situ with the image, it's really tiny, 0.05%. It's the error in reconstructing the geometry in situ with respect to the best work that you can do offline using tomography. So at the end of the story, which is the ground truth at this point in time, and the assisted solution. Clearly, you can just think about what we're doing, and what about moving to 3D, not just, let's say, layer-wise and very simple cubes. So if we have manifold, or we can even create these complex shapes, these empty eggs, somehow we have been doing some work, and it's published on Technometrics on doing the similar job for 3D printed Voronoi eggs, just to say that complexity in shape can be really amazing in terms of the type of techniques that are needed to solve the problem. We have been recently also presenting a paper in the IISc transaction that is taking advantage of some solution that was proposed by Boy and Apley for textile, but this is applied to textured surface for 3D printed with extrusion, where you have this random texture, but sometimes in the random texture you have also some defects, and you should be able to detect this deviation and this error, this anomaly, just by also considering this, let's say, layer by layer variability due to the texture that is, the in-control texture is something you cannot avoid. And in this case, we have been applying random trees plus clustering, obtaining some interesting results. Just few comments on video. I will have no time, but there's, let's say, just I want to point out that there are quite interesting problems also coming out in video. The first problem we have been solving is hotspot detection. So the laser is moving, he's doing his job, but sometimes one point remains hot for a longer time, and this is a problem at the end. And we were able to define, let's say, some sort of control chart able to detect this persistent, let's say, energy and intensity in one specific location. You see that here the process is really dynamic, it's really chaotic, because this is how the process is working. So traditional solution for SPC, I mean, are not going to work. And is also interesting, the contamination that is coming from AI. So we have been basically publishing 3 approaches for solving this hotspot detection problem. The first one was based on spatially weighted principal component analysis. The second one, it's a spatial temporal statistical process monitoring solution together with Jan and Painabar and Marco Grasso, so the group of Georgia Tech. And the last one, it's just using some pure, let's say, neural network solution with some super vector machine idea, just to say that you can maybe solve the problems with different perspectives and different angles with many different solutions. And sputtering is also quite an interesting stuff. I know that a lot of people now is interested in this sputtering. The idea is, in this case, I can take some sort of, let's say, sputter signature, and if I'm able to model the sputter signature during the video, so how many, let's say, chaotic stuff are coming out from the process, I can, at least in principle, predict some defects in the part at the end, because it is shown, even with some sort of knowledge of the process, that if there are a lot of sputtering, we are going to experience some porosity at the end. I will not go in deeper detail. There's a paper out that is quite, I think, interesting, and the way in which we have been solving the problem, again, it's moving the sputter phenomenon in the profile, and for solving this translation of the sputtering in profile, we have been using the replay gain function, but there's a lot of opportunities around this area. It representing point process with the function, and then playing just with the function and the functional analysis. I will skip the part because I think I'm running out of time. Just to say that there are a lot of opportunities that we are exploring. Similarly, in bioprinting, all this image stuff, it's going to be a little bit more complex because unfortunately bioink are transparent, and so there's this additional challenge. There's some dynamic that you want to detect in real time to avoid defects, and this can be done just as you see, just by looking to thermal videos that are trying to capture the dynamic. And one new, let's just a comment, one direction that is totally, let's say that just in bioprinting, we didn't see anything similar in additive manufacturing, is the monitoring of cells. So these small dots with different intensity are the cells that are being deposited, and maybe you can do some sort of SPC for trying to see how the cells are located during your 3D printing process, if there's some homogeneous spreading of cells inside or not. And maybe in the future, we will also be able to understand if the cells are viable and have not been damaged by the process. Two comments at the end. We are interested now, and we're working and doing a lot of work on transfer learning, because there's a lot of interest in changing, let's say, and being able to investigate if I'm moving from one material to another, what is the type of knowledge in terms of process response to process parameters. So the quality of the part with respect to the change of process parameters, how this process printability map change when I'm changing the material. And we saw a lot of interesting results in transfer learning. A final comment, and I've done a lot of data. There's a lot of new AI solutions. This is more for the industries, I should say. I saw a lot of interesting use of AI tools, but sometimes I see also some abuse, even in, let's say, fitting on predicting and modeling very, very simple shapes. There's this huge black box. You don't really understand what's going on, but maybe the type of connection between the response and the process is quite simple to be modeled with existing solutions. So I will really want to point out that there are a lot of advantages, but also some cons in moving in this direction. And the last comment is that all this type of stuff, being able to produce zero defect, avoiding defects, avoiding flaws, it's supposed to go in the direction of green manufacturing, sustainable manufacturing, because I'm basically avoiding to waste resources, time, and material, because as soon as I see a defect, I can stop the process. But on the other side, the digital side and all the computation are taking a lot of energy. So this, it's very, let's say, hot in the manufacturing sector, this twin transition, digital plus green. I should say that they are friends, but they are also enemy. So again, if you are using a lot of energy for doing a deep neural network just for fitting a straight line, maybe this is not going to be in the right direction for sustainable manufacturing. This is my last slide, I think, and I want to thank you for the attention.
All right. Thank you, Dr. Colissimo. That was a really amazing talk, covering a lot of areas there. Just as a reminder to our audience, if you do have a question, you can put it in the chat. There's also a question section there where you can post your questions. I will be monitoring those. Right now, oh, there was a question. Let me see if I can pull this up. A little bit hard. There's something about, so we have a question here. Were you able to perform any probability of defect detection studies on the in situ inspection?
Say it again, probability of?
So the question is, so they said it was a very interesting talk. Were you able to perform any probability of detection or defect detection studies on the in situ inspection?
Yeah, this is exactly the last work we have been doing. We have been fitting this probability of detection curves, and this is going to be possibly out in a journal paper in the hopefully this year. And so I think it's quite important for the companies to see how good you are in detecting defects as a function of the size of the defect. Clearly, there's a lot of new space for estimating this probability of detection, because they can even depend on the type of techniques you are using for the image analysis and for detecting the anomaly. So it's also interesting to see how this probability of detection changes depending on the type of solution for the anomaly detection, or let's say out of control detection that you are implementing. And so I think there's a lot of space for going in this direction with many different type of image analysis and let's say control chart or anomaly detection solution, to see how this probability of detection change depending also on the data mining and data analysis technique that you are using.
Okay, great. And that question was from Pete Loftus. So thank you, Pete, for that question. While we wait for other questions, I did have sort of, well, maybe it's a question of clarification. I wouldn't say clarification, but so recently, related to a different area, sort of animal conservation area, I've been starting to dabble in statistical shape analysis. And I was wondering if you, I noticed throughout your talk, there was a lot of talking of deviations in geometry, so accounting for the shape. I wonder if you've had any experience in sort of adapting statistical shape analysis or some of those techniques in this work that you've been doing.
Yeah, we've been doing some work on statistical shape analysis together with Enrique del Castillo some years ago, and trying to apply to, let's say, 3D point clouds, complex or non-complex. We have been even moving to manifold, and I found this to be a really elegant and quite useful technique, because there's a lot of interesting stuff. So for sure, it's a good way for solving and trying to model in this sort of SPC-like or even analysis the effect of process parameters. I remember there was a paper a few years ago, I should say, something like 10 years ago, and they were applied. We started applying these to 3D point clouds for cylinder, and then we moved to manifold. Frankly speaking, when the parts are so complex, like for instance, the Voronoi eggs that I've been showing, full of empty space, I don't know if statistical shape analysis is able to capture all this complexity.
Okay.
But for piece, let's say, or detail, I think it's going to be quite interesting technique.
Okay. Good. Thank you. Let's see. I'm monitoring here. So far, oh, there we go. So we have a question here from, let's see if I can, from John Liu. So he said he missed the slide on 3D printing error analysis. A general question that he has is error depending on the shape of the underlying object?
Yep. This is what is making all the additive manufacturing, I think, a lot of fun, because there are a lot of different sources of problems. I should say material, process, design. Process, I mean process parameters, design, and shape. So when you are moving from one shape to the other, maybe because additive allows you to have some customized production, the problem is that each time for you it's the new time. I mean, because the key point is how I can move all the knowledge that I had and that I gain working on a different shape now that my shape is different. And so there's a lot of interesting study. There's one recent work of the Oak Ridge National Laboratory that is doing the job of creating some voxel that are also including as covariate some sort of relevant information on how the voxel relate to the overall shape. So the voxel basically saying I'm close to the border, I'm in the middle, so I'm on an overhang, I'm not in overhang. So some sort of relevant shape-based information for being able to make this mapping between the voxel, the in situ monitoring signal at that voxel, and what is the end of the story in terms of the quality of the voxel. So if the voxel, for instance, is full of pores or not. So this is an interesting kind of way of modeling or creating an approach that it's standardizing with respect to the shape, this shape dependency. We have been always trying to do some, as you saw in the video, complex shape just to play in the game and see how the shape is affecting the final shape, the final defect. And we have been working with these metrics of deviation with respect to the nominal, max deviation with respect to the nominal. There is some sort of shape agnostic defect, but there's a lot of, let's say, interesting connection between geometry and probability of defect.
Okay. Thank you. Okay, so no questions yet. So with that, so we still, of course, have time for some questions. So if you have those, you can put them in the questions or in the chat. But if not, I will probably start to wrap things up here. So again, thank you, Dr. Colosimo, for this excellent webinar. We do have a recording of this, so we should be posting that here soon afterwards. If you happen to miss some of it, or you have a colleague who might be interested, again, let them know. And again, be sure to check out the International Statistical Engineering Association website, ISEA-Change.org. And with that, I think I will go ahead and close this out. So thank you again, and thank you everyone for attending.
Thank you. Thank you. Thank you. Thank you for your time. Thank you.